Hi, so this is Simon Apers. I'll be giving a talk about some joint work with András, Gilyén and Stacey, Jeffery called a unified framework of quantum walk search. So we'll be talking about graphs G with nodes at V and edges at E, where the nodes correspond to vertices of the graph and the edges are just unordered pairs of nodes. Now, a random walk on a graph like this looks a bit like this, right? We have some initial node x0, which we'll call S. Then we pick a uniformly random neighbor of our initial node, which could be x1. We pick another uniformly random neighbor, x2, x3, x4, and so on. So basically, we get a stochastic sequence of states corresponding to vertices of the graph. And one of the quantities that one is typically interested in is what's called the hitting time. Now, what's the hitting time of a random walk? It corresponds to the expected time for a random walk starting from node S to hit a marked set of elements M. Basically, it's the expected number of steps that you have to take before our random walk is in a state which is inside the marked set M. Now, why are we interested in things like random walks, hitting times, and so on? One is that they're a great source of very nice mathematics. They form a natural way to study graphs, but also electric networks and so on. Second is that they're a source of great algorithms. So they're a building block of many algorithms, amongst which is the ST connectivity algorithm in log space. Now, this talk is not about random walks or hitting times, it's about quantum walks. So what are quantum walks? You can think about them as random walks, but now every state at any time step is a quantum state, which is a superposition over vertices of the graph. So basically, we start in some initial quantum state, which could be localized at a single node. And then next state will be superposition over neighbors of that node. And this could sort of evolve throughout the graph. So at any time step, the state of our quantum walk is a superposition over different nodes of the graph. Now, we're also interested in this notion of hitting time, where we start from a quantum state which is localized on a node S, and it evolves, and we're interested in the time it takes for the quantum walk to hit the set M. Now, I'm putting hit between quotes because in contrast to classical random walks, the state of the quantum walk is a superposition. So a state could be partially inside set M and partially outside of it. So basically, you can think about the quantum walk hitting time as the time it takes for a quantum walk to have large overlap with the marked set, if you want. Now, why are we interested in such things like quantum walks and hitting times of quantum walks? Again, they're a source of great mathematics. Some examples are that it's very natural, they form very natural application of Jordan's lemma. And there's again a very close relationship to electric network theory. Second is that they're also a tool for constructing great quantum algorithms. The key here is that quantum walks can actually speed up the random walk hitting time in an appropriate sense. This is the source of quantum algorithms for element distinctness by Ambenis, quantum backtracking by Montanaro, and many, many more. So let's get a bit more formal. We considered the two following problems. One is we are given now, instead of consider a single initial node, we consider a distribution sigma, and so we assume that x0 is distributed according to sigma. So on the classical front, we are given a initial vertex which is distributed according to sigma. We can use a random walk, and we want to find a marked element M. Quantumly, we start from a quantum state psi 0, which you can think of as a quantum encoding of the state sigma. In some sense, if sigma is uniform distribution over a subset, then sigma will be uniform superposition over that subset. And starting from this state, we want to use a quantum walk to also find a marked element in the set M. Now that's what we want. And what are the costs that we care about? We split these up quite canonically into the setup cost, the update cost, and the checking cost. So what are these? In a classical case, which forms the left column here, the setup cost is basically the cost of sampling an initial node according to distribution sigma. The update cost is that of implementing a random walk step, so in some sense updating the state, where we want to sample a node y from the neighborhood of x. And then there's the checking cost, which is the cost of checking whether a certain state is inside the marked set or not. Quantumly, the setup cost corresponds to creating the quantum state that describes or that corresponds to a distribution sigma. The update cost corresponds to mapping the node X to superposition over its neighbors. And finally, the checking cost corresponds to mapping a state corresponding to a node Z to minus that state if Z is a marked element and leaving it invariant otherwise. This is in some sense a quantum version of a checking operation. And what we want to do is we want to find marked elements whilst minimizing these costs. So classically, for random walks, we can distinguish two kind of canonical algorithms. One of them is a hidden time algorithm, where we just naively start from some state S, distributed according to sigma. So this has setup cost S. Then we check whether we have a marked element or not, and if we don't, we update the state. So we implement the random walk, we get a new state x1, we can check, if not marked, we update, and so on. Now the expected number of times that we have to repeat this is what we call the hidden time, right? And so the total cost of this scheme is S, once the setup cost, plus the hidden times time check plus update. But it's not the only algorithm, and in some cases, we might actually prefer a different kind of algorithm, which we call the mixing time algorithm. Now for that, I'll first define some things. One thing is the spectral gap of the random walk, and I'll loosely define it here as basically the number of updates that we have to do, so that starting from any state X, the state Y, that's the resulting state after 1 over delta steps, is approximately distributed according to pi, which is the stationary distribution of the Markov chain. So you can think about 1 over delta as essentially denoting the mixing time of the random walk. I would also define epsilon as being the probability of getting a marked element if we sample a state according to the stationary distribution. Then one can show that the hidden time is at least 1 over epsilon, but it's also at most 1 over epsilon delta. And the second inequality actually follows from the following argument, and this is what we call the mixing time algorithm. So we start from x0, which is distributed according to sigma. We check whether it's marked or not. If it's not marked, now we implement 1 over delta steps. The thing is that after 1 over delta steps, we get a new state x1, which is now distributed approximately according to pi. And hence, if we repeat this, then these individual samples correspond to draws from the stationary distribution. And the number of draws from the stationary distribution before we get a marked element is basically 1 over epsilon. So 1 over the stationary probability of the marked elements. Now the cost of this scheme is S, the setup cost, plus 1 over epsilon times delta times U, because we basically have to repeat 1 over epsilon times this thing, plus 1 over epsilon times the checking cost. And this is incomparable to the cost of the hidden time algorithm, because the hidden time is upper bounded by 1 over epsilon delta, but it's lower bounded 1 over epsilon. So if, for instance, the update cost is very large, then we'll prefer this algorithm. Otherwise, we'll prefer this algorithm. Now, quantum walk search algorithms are kind of form sort of analogon of that. And you can think about them as Grover search on graphs, right? So in '96, Love Grover proved that quantum algorithms can quadratically speed up search on a database. So we can find a marked element among n elements in square root n queries in some sense. Now in '03 and '04, this was generalized to a quantum speedup for search on graphs such as lattices, Johnson graphs, hypercubes, and some more, where the algorithms were analyzed using sort of an ad hoc analysis where they largely relied on the symmetries of the graph and so on. But in '04, quantum walk speedups were proven for more general graphs. This was initiated by the seminal work of Mario Segeti in '04. But then there's also Crovy, Magnes, Ozols, and Roland. And most recently, Ambenis, Gilyén, Jeffery, and Kokanis, who showed that if sigma, the initial distribution, is equal to the stationary distribution, so this is a special case, then we can find a marked element in a quantum complexity, which is S plus square root of the hidden time times U plus C. This compares to the classical hitting time algorithm, which is S plus hitting time of U plus C. In a different work by Mañez, Nayak, Rolla, and Santa in 2006, they proved that again, if we start from the stage theory distribution, that we can find a marked element in setup cost plus 1 over square root epsilon delta U plus 1 over square root epsilon C. And this is in some sense a quantum version of the mixing time algorithm, where we get square roots over these complexity bounds. And then there are two more works that I'll mention. One is by Beloff in 2013, who showed that now not only for sigma equal to pi, but actually for any sigma, we can do something quantumly. And he showed that it's possible to detect whether the set of marked elements is empty or not in S plus square root CT U plus C. And CT here is something that we'll call a generalized commute time. And I'll go into details of that later. But this basically generalizes the previous results because it's equal to the hitting time if sigma is equal to pi. But it doesn't completely generalize the previous results because it only detects whether a marked element exists or not. Now, this is something peculiar about quantum walks and quantum algorithms more generally, whereas the classical algorithm can only detect whether a marked element exists or not by finding one. Quantumly, it's actually possible, and this is exactly what happens in this algorithm, that we only detect the presence of a marked element without actually finding it. And then finally, there's this very nice work by Dohotaru and Hoyer from 2017, who showed that under even more constrained conditions, namely if sigma is pi and there's just a unique marked element, then we can find this marked element in time, which is setup plus square root of the hitting time times U plus 1 over square root epsilon times C. And this in some sense has the best of both worlds, right? If you think about both previous algorithms, this one had square root hitting time, and this one had 1 over square root epsilon times C. And these are actually the two optimal costs. And this compares to the classical algorithm, which also exists in the case when there's a unique marked element. Now, this summarizes these four different quantum walk algorithms, which kind of results in a bit of a gapped framework where many approaches are incomparable and cannot be understood using a single algorithm. Now, what we did is we actually unified all these algorithms into a single quantum walk algorithm, and we actually improved certain algorithms as well. So what do we prove? We prove that there exists a quantum walk algorithm that finds a marked element, so not only detects it, so we actually improve this column to all finds, in a quantity, the complexity, which is called S plus square root of CT of tau, which I'll call the generalized tau commute time, times square root tau U plus C. And we do so for any sigma, right? So here we get for any sigma. And for specific parameter choices, this reproduces any of these four existing results and kind of combines them into a unique framework. To go into a bit of details, let's consider the special case where sigma is equal to pi. Then we get to this generalized tau commute time actually equals the hitting time of p to the tau. So if p is the random walk transition matrix of a normal random walk, p to the tau is a transition matrix of taking tau steps each time. So in some sense, we can consider the algorithm where we start from x0, we apply tau steps and then check, we get x1 and so on, and we repeat this until we find a marked element. Then the expected number of iterations here is the hitting time of the tau step random walk. And we can expect that this goes down, right? So in this plot, that's exactly what we're showing. We're showing the hitting time of the tau step random walk as a function of tau. So if tau is equal to 1, we just get the hitting time. If tau is equal to 1 over delta, we get 1 over epsilon, which is basically the mixing time algorithm that we discussed earlier. And then this Dohotaru-Hoyer result is in between here. Now what we show is we actually show sort of a continuous interpolation between all these frameworks as a function of this parameter tau. This was for a special case where sigma is equal to pi. In another special case where tau equals 1, but sigma is general, this generalized tau commute time is actually equal to the generalized commute time, which I call CT. And this generalized commute time shows up in Beloff's work, where he showed that you can detect in S plus square root CT U plus C for any sigma. And I mentioned that this is a shortcoming of Bellows, right? You can only detect. Now our work improves this detect to find. We actually find a marked element for any sigma in the same complexity. That is up to polylog factors. Independently, this result was also proven by Stephen Piddock in 19. Now, as an example of this generalized commute time, that's also why I call it generalized commute time. If sigma is localized on a single element, then CT, this generalized commute time, is actually the normal commute time, which corresponds to the expected time to go from S to a marked element and back to S. Now, I'll note that a classical algorithm has complexity hitting time from S to M, whereas we get square root of the commute time from S to M. So it is possible that our quantum algorithm is actually slower than the classical algorithm in certain cases. And in these cases, of course, we do not get a quantum speedup. We get two more additional results, which are that in the special case where tau is 1, we only need quantum walks. So what do I mean by that? The preceding algorithms all required a sort of involved technique called phase estimation or quantum fast forwarding. We show that this is not necessary. And this answers an open question of Untitled, Gilyén, Jeffery, and Kokanis from 19. And then we also prove certain Monte Carlo type bounds. Now I'll sketch a bit the proof ideas that we used. And specifically, I'll do that for our algorithm that finds a marked element in square root of the generalized commute time. So what's the idea of the proof here? We build on a technique by myself and Saarland from 18, where we show how to map a general initial quantum state psi to the state p to the t psi, where p is the classical random walk transition matrix, plus some perpendicular state. So in some sense, we are implementing the t-step random walk as a quantum state. And we can do so in O square root t quantum walk steps. So I'm hiding polylog factors here. So in some sense, we're quadratically improving the runtime of the classical random walk. But of course, what we get is this sort of quantum state. We don't get the classical distribution. And that is actually a limiting factor. So we have this. What we then go on to show is that if we take a general random walk, which starts from a state which is distributed according to sigma, and it commutes between sigma and m, so basically it goes to m and then revisits the support of sigma in OT steps, then this quantity, basically this is, recall that this is the quantum state that we can construct. The projection onto the marked elements in 2 norms squared will be large. Now, how should we read this? So this is the quantum state that we can construct, and this is the projection onto the marked states. This basically implies that if we measure the quantum walk after t steps, then we will find a marked element with constant probability. So as a corollary, this proves that we can find a marked element m, which is a consequence of this fact here, in square root of the sigma m commute time, where the sigma m commute time is, like I mentioned here, basically the time to go from sigma to m and back to the support of sigma. Now, this is not quite what we wanted, because there was this initial work by Bellows who showed that not only can we get a quadratic speed on the combinatorial commute time, but he used this electric networks quantity. So for that, we used the second claim, which was known for special cases only, that this combinatorial quantity called the sigma m commute time that I just defined is approximately equal to this generalized commute time, which is an electric quantity. I will use electric networks theory to prove that. And as a corollary, we can find a marked element now in square root of the generalized commute time quantum walk steps. And this now strictly generalizes Bellows' result. Maybe a second technique that I want to highlight, and this will be the end of my talk, is how we answer this question of Untitled, Gilyén, Jeffery, and Kokanis on avoiding quantum fast forwarding. So recall that quantum fast forwarding, starting from this initial state sigma with some 0 register, applies the t-step transition operator onto the state plus some orthogonal register. And what our quantum walk algorithm does, it implements this quantum fast forwarding algorithm, and then it just measures this first register. And we prove that this returns a marked element with high probability. Now, if we pre-open this black box of quantum fast forwarding, it actually looks like this. So recall that this full picture here is quantum fast forwarding, right? It maps sigma 0 to this pt sigma 0 plus some orthogonal state. What it actually does is it first puts the second register in a superposition of square root alpha L times L. Then in the second step, conditioned on this L, it applies the quantum walk operator, which I'm denoting by W, L times, and then it implements the inverse operator of this first operation. And there's basically some linear algebra that shows that this results in a linear combination of these quantum walk operators. And we can choose these alpha L's in such a way that this operator approximates p to the t. So this is all still a bit abstract, but it's in the end, it's all linear algebra. This is what happens inside QFF. And then we just measure the first register and recall that this returns a marked element with constant probability. Now, however, we can notice that since in the end we only measure the first register, this operation and this operation commute. So what does that mean? It means that we might as well first measure and then apply this operator. But we only care about this measurement, so we might as well drop this second operation here. This results in the following algorithm, which you can show will yield exactly the same outcome. So we just apply this one operator, then this controlled W operator, and finally we measure the first register. This actually corresponds to, so since we just measure the first register, we might also measure the second register afterwards, which also commute with this. But if we measure the second register, then we'll get back W to the L sigma with probability alpha L. This follows from Born's rule, which basically says that we'll retrieve this state with probability equal to the square of this element. So with probability alpha L, so basically the scheme is equivalent to implementing the operator W to the power L psi with probability alpha L. And this is actually what the simplified algorithm now does. So what we proved is that this full scheme, which was actually quite long, actually is equivalent to just implementing this operator W to the L with probability alpha L. And this gives us the following equivalent algorithm. We might as well pick a parameter L between 0 and square root t with probability alpha L, then apply L quantum walk steps, where L is this random variable. So that maps sigma to W to the L sigma. And finally, we can measure this state. And since the original algorithm returns a marked element with constant probability, also this algorithm will do so. So that concludes my talk. I thank you for your attention, and I thank you for watching.